This is Algebra 2 at Trig, 9.4. We're talking about dependent events. Before we get into that, we're going to work on some factoring. So there's our first warm-up question. So work on that factoring. You can pause the video, come on back, and we'll talk you through it. So here we're looking at 4x to the fourth minus 11x squared minus 3. We're going to multiply those two numbers together. We're looking for a multiple of 12 that adds to be negative 11. You know the two numbers have to be different to multiply to be negative 12, and the larger number has to be negative. So 1 and negative 12, 2 and negative 6, 3 and negative 4. Those are the only ways to multiply to be negative 12. And there's only one of those ways that add to be negative 11. So we're, of course, going to use this. Now we have to decide, are we going to use guess and check, or are we going to use factor by grouping? If you like to use factor by grouping, we would take our 4x to the fourth and our positive x squared, because we're going to use the 1, and our negative 12x squared, because we're using the negative 12, 1 and negative 12, because that multiplies to be negative 12 and adds to be negative 11. And then we put the negative 3 at the end of it. Because I can put my table here. So we're going to factor by grouping. We circle both pairs there. Pull out what the common factor is. That would be x squared. That would leave me a 4x squared and a positive 1. Positive 1 on 11. Bring down your sign. The common factor there is 3. 3 times 4 makes 12, x squared. 3 times 1 makes 3. A negative and a positive make a negative 3. Notice my parentheses are exactly the same. So we can say x squared minus 3 and 4x squared plus 1. That's using factor by grouping to help you factor a trinomial, a quadratic. Well, this is to the fourth power, but it acts as a quadratic because the exponents are halves of each other. So it's still a quadratic pattern. Neither of these can be factored further. So we're all done. Okay, looking at our next binomial. I look at the binomial and I see that the exponent on the 4 is an even number. Okay, it's a 4. It can be considered a perfect square. This is a negative. So this is the difference of a perfect square. But unfortunately, the 12 and the 3 are not also perfect squares. So this is not the difference of two squares. It's almost, but not really. But then you may notice that a 3 can be divided into both of these. So we're going to factor that 3 out. Don't throw it away. You have to keep it. There I did my GCF. I pulled the 3 out. Now I have something that's a perfect square and something that's a perfect square. So I can do the difference of two squares. 2x squared plus 1, 2x squared minus 1. It doesn't matter which one has the plus or which one has the minus. because all the numbers are the same. You can FOIL it together to see if you get what you started with. 2 times 2 makes 4x squared. 2 times 1 and 2 times 1, a negative and a positive make none in the middle. And 1 times 1 makes 1. Now you can check your work. You know if you did it right. That's factoring. We can do this one with factor by grouping, like I showed you. There's also a method of guess and check. That's when you just throw your parentheses down. Okay. I would probably, if I was just randomly guessing, I would probably start with 2x squared and 2x squared. That would be my first guess. Now I have to come up with 11 by doing these two numbers. But unfortunately, I can only have a multiple of 3 on the last two numbers. So that has to be some sort of 3 and 1, so that's not working. That's 6 and 2. I can get to 4, I can get to 8, but I can't get to 11. So that's not working. That guess didn't work. So my other way to say 4x squared and x squared. That's the only other option I have. Because my outer and my inner have to have like terms that are both going to be squares. So that's why both the x's have to be squares. Now, my table is telling me I need to get a 12. A 12 would be 4 and a 3. A 1 is going to be a 1 times a 1. That gives me 12x squared. That is negative. And a positive 1 will add together to give me negative 11. So there's my guess and check method of doing it. Either way works. That might be more confusing because more is going on in your head. So I do like to offer factor by grouping. It shows everything you're doing. It takes care of it. Get your answer every time. Let's move on to dependent events. Okay, two events, A and B, are dependent events if the occurrence of one affects the occurrence of the other. Listen to that carefully. Yesterday we had independent, and that's when the occurrence of one did not affect the other. Today we have dependent, where the occurrence of one does affect the other. The probability that B occurs, given that A occurs, is called a conditional probability of B given A. And that's written as a probability of B. Then we put a bar in the middle, A. And that bar is standing for the word given. B given A. B given that A occurred. So the formula we're going to end up using for A and B, and that's assuming that you're going in this order, is a probability of A times, because you want both things to occur, it's an and statement, so it's always times, the probability of B given that A happened. And mathematically, it looks like we can manipulate this and we can divide the probability of A underneath probability of A and B. And if we did that, we would get the probability of A and B to be divided by the probability of A. So we're going to come down here, and here's a problem that deals with a table. Many of these questions deal with a table. they tell us that there's going to be 200 registered students in this college. Must be a pretty small college. Or it's in thousands, who knows, whatever. So we're going to add these numbers together. 80 plus 40 is 120. So there's 120 females. There's 80 males. Together they're adding to that 200 number. There's 200 registered students. Some of those students are part-time, some of those students are full-time. The part-time students is 140. The full-time is 60. Together, they're adding up to 200. Pretty straightforward. So, let's say you're the registrar or the counselor and you're trying to find the probability that you select a female. So you could say that you have all 200 college students in a filing cabinet. What's the probability that you are going to draw a female out of that group? That's favorable out of possible. That's 120 females out of 200 possible students. Pretty straightforward. That's the probability of a female. So you could cross the zeros out, and you're left with 12 and 20. So that would reduce to be 6 and 10, 3 and 5. So 3 over 5 is our probability. Now here's where the good stuff starts. What's the probability given you're only looking at full-time students? So you go to this filing cabinet I've been talking about, and you go to the drawer that's only full-time students. So the drawer that has full-time students, those are the only ones we're looking at. We want the probability of a female. Well, there's 40 females out of the 60 possible full-time. Given you're only looking at full-time students, what's the probability of a female? And that would reduce to 2/3. What's the probability if you look at all the folders, because there's no given, there's nothing to cut it down, it's just probability of part-time. The part-time, there's 140 of them out of the 200. Cross the zeros out, you're left with 14 over 20. Half of 14 is 7. Half of 20 is 10. So you got 7/10, 70%. A male given a part-time student. You're only looking at part-time students. So if you go to the drawer in the filing cabinet that only has part-time students, the males, there would be 60 of them out of the 140. Cross the zeros out, you're left with 3 over 7. All right, on the flip side, we're taking an observation. So you could call this experimental probability. Using observations made of drivers arriving at a particular high school, the study reports that 69% of the adults wear seatbelts while driving. So we come down here to our tree diagram, and we identify that the probability that an adult wears a seatbelt is 0.69, so the probability that they do not wear a seatbelt would be the complement of that, 0.31. because together that's 100%. You're either wearing the seatbelt or you're not wearing the seatbelt. You could say they're complements of each other. A high school student in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. So we come down here and we say that the student wearing the seatbelt is 66% of the time. That's not 66% always. That's 66% of the 69% that the adult is wearing the seatbelt. They only wear it 69% of the time. They wear it 66% of that amount. But wearing it and not wearing it have to be complements. So that's going to be 0.34. %26 of the time, when an adult does not wear the seatbelt, the kid does. So 20, did I read that right? 26, there it is. And 26% of the time when the adult does not. So we get 74% of the time they're not wearing it when the adult is wearing it. So we've drawn a tree diagram where the probabilities are given on the branches. Notice that the probability of all the branches from the same point add up to 100%. These two are adding up to 100%. 100% and 100%. You're either wearing the seatbelt or you're not wearing the seatbelt. The only two options we've got. So what's the probability that a student wears a seatbelt? Just to answer the question, students in the study wears a seatbelt at what probability? Well, we have two scenarios going on. We have data in this situation, and we have data, or we have data in this situation. So, the probability of A and C, A is that the adult wears it, C is if the student wears it when the adult wears it. So that is 0.69 times 0.66. Or you could look at it from the point of view when the adult does not wear it. 31% of the time, the student wears it 26 of that 31. So 0.69 times 0.66 plus 0.31 times 0.26. So in this study, 0.536. So hopefully you understand, not from this survey, but the importance that you should be wearing your seatbelt regardless. Even more important, or just as important, in the back seat. You'll get your cage rocked either way. You're not that much safer sitting in the back. The front seat belts, the cars currently beep if you're not wearing it right. So I would assume if we took this survey nowadays, you would have more adults wearing it because the beeping of the car typically goes off continuously until you do. Okay, now we can extend this when we have more probabilities. The formula for finding probabilities of dependent events can be extended to 3 or more events. Your teacher passes around a box with 10 red pencils, 8 pink pencils, and 13 green pencils. If you and 2 friends in your group are the first to randomly select pencils without, there's your dependent right there, it tells you, that's the most important word we got going, without finding, or without putting them back, what is the probability that all 3 of the students get pink pencils? So pause the video, give that one a try. You got to take time to read it, make the decisions on your own. Then we'll talk about how we set it up. So a very important part here is to see about the total. The total number of pencils would be the 10 plus the 8, which is 18, plus 10 more, which is 28, plus 3 more, which is 31. There's 31 total pencils. Probability, pick 3 consecutive pink pencils. So we have 8 pink pencils to start with. So there's 8 out of 31 pencils available for the first person. Then there's 7 out of only 30 because we did not return them. This is what makes it this is what makes it dependent. Now there's less pencils. The probability is changing for each person. Then there's only 6 pencils in there out of 29. 6 pink ones out of 29 total. So we have 8 times 7 times 6. And 31 times 30 times 29. So we can take our 336 and divide that by the previous number. That can get us a decimal. And if we hit the math key and the fraction, it will reduce that fraction for us. So we don't have to worry about being aware of our factors. So that gave us the probability of 0.0125. If we were interested in the decimal. So that is dependent because the number is going to change, especially in the denominator. Here, we're randomly selecting cards. What's the probability that the first card is not a heart and the second card is a heart? We're going to do 2 questions. We're going to do one where we replace the card, put the card back in the pile, and then we're going to do the question again where we do not replace it. This one is independent. A is independent. B is dependent. So A is going to be independent. Probability of not a heart, then a heart. So not drawing a heart is 39 out of the 52. 39 cards are not hearts. 13 plus 13 plus 13, the other 3 suits. And then the probability that you get a heart, you're returning that card, right? We're replacing it. So there are 13 hearts out of still 52 cards. That's 3/4 times 1/4, which is 3/16. 3/16 is approximately 0.1875, or exactly, in this case, it's exactly 0.1875. Now let's take a look at the probability if you do not return it. So this one is dependent. When you do not replace the card back in, you're still doing probability of not a heart. Then you're going to get a heart. That storyline is the same. So it would still be 39 out of 52 for not the heart. Still 13 hearts. But there's only 51 that is in the deck now because you did not return that card that was not a heart. That's 3/4 times 13 out of 51 hearts. So that's 39 out of 204. 39 divided by 204 is approximately 0.1912. So you can see it's not much better chance, much more likely, but it is more likely.